A dog chased a cat. Picture it. A cat chased a dog. Completely different scene. But look at the words. Exactly the same 5, just rearranged. The only thing that changed is the order. To a human, that's obvious. To a transformer, it's a genuine problem. Because a transformer doesn't read left to right, it takes in every word at the same time, in parallel. So how can it possibly tell these two sentences apart? The answer is a clever trick called positional encoding, and by the end of this video, you'll know exactly how it stamps order onto words that are otherwise processed all at once. Here's the root of it. A transformer processes all the words in parallel. There's no conveyor belt, no built-in sense of first, second, third. So instead of feeding position in through the order, we bake it directly into each word's vector. We add a position signal on top of the meaning. Embedding, which carries meaning, plus a positional encoding, which carries place, equals the vector the model actually reads. That one addition is the whole idea. Here's the picture we're heading toward. This cyan dot is the word dog, sitting in position 1. Now here's the same word dog in position 3, a different point in the space. Same word, but a different location depending on where it sits in the sentence. And the shift is gentle. Close enough that it's still clearly dog, but different enough that attention treats the two as distinct tokens. Position becomes part of the geometry itself. Let's build exactly how that shift is computed. Here's the plan. First, why attention is order blind in the first place. It turns out to be a direct consequence of the weighted sum from the attention video. Second, the sinusoidal encoding itself, sine and cosine waves, and will compute real values as always. Third, a trace along. We'll stamp a position onto the word dog, step by step. And a bonus after the cheat sheet, learned versus fixed encodings, and the modern approach called RoPE that today's models actually use. This one builds straight on the vectors video and the attention video. So keep those fresh. Quick refresher from the vectors video. An embedding turns a word into a learned vector. Just a list of numbers. Dog might be 0.2, 0.9, 0.5, 0.1, and so on. And the key property, distance equals meaning. Dog, puppy, and canine sit close together. Cat is nearby. Carburetor is far away. It's learned during training, not looked up. And crucially, it's the exact same vector for dog, no matter where dog shows up in a sentence. And that last part is exactly the problem. A plain embedding carries meaning, but it carries no position at all. Every dog looks identical to the model. Now, the crux, and it comes directly from the attention video. There, a word's new vector was a weighted sum, sigma of weight times value, added up over all the words. And here's the mathematical catch. A sum doesn't care about order. 3 plus 5 plus 2 equals 2 plus 5 plus 3. Shuffle the terms however you like. Same total. So if dog and cat carry the same query, key, and value no matter where they sit, attention just blends the same ingredients in the same proportions, regardless of arrangement. Which means dog chased cat and cat chased dog look like the same bag of words, and attention produces an identical output for both. Attention on its own literally cannot tell those two sentences apart. We have to break that symmetry by making each position different. Let's see the fix in miniature. Without position, dog chased cat and cat chased dog are the same set of vectors, so attention gives them the same output, a failure. The model is blind to which animal did the chasing, but if we stamp a position onto each word, so dog in slot 1 is a different vector from dog in slot 4, the symmetry breaks, and the two sentences finally look different. That single stamp turns two identical bags of words into two genuinely different inputs. So the entire job boils down to one design question. What should that position stamp actually look like? Let's reason it out. Before waves, 2 tempting shortcuts, and exactly why they flop. Shortcut 1, just tag each word with its position number, 1, 2, 3. But by word 5,000, that number is so huge it completely drowns out the word's actual meaning. Shortcut 2, fine, squeeze it between 0 and 1. But then halfway through is a totally different spot in a 5-word tweet versus a 500-word essay. The model can't trust it. Both shortcuts flop. So what do we actually want from a position stamp? 3 things. The stamp must stay bounded so it never explodes. It must be unique for every position. And the spacing between positions must stay consistent, no matter the length. So, what kind of thing wiggles in a bounded, repeating way and never blows up? A wave. Sine and cosine, specifically the trick the original transformer used, and it's beautifully simple once you see it. Here's the design. We use a whole set of waves at different frequencies. This cyan one is low frequency. It changes slowly as you move across positions. This violet one is high frequency. It flips back and forth quickly from one position to the next. Each dimension of the positional encoding is its own wave, running at its own frequency from very slow to very fast. Now read all those waves at a single position. Take one vertical slice, and you get a unique pattern of values. That pattern is the position stamp for that spot. And there's a lovely division of labor. The low-frequency waves tell you roughly where you are. All the high-frequency ones pin down exactly where. Together, they locate any position precisely. Now the shorthand for the stamp you just designed? Here's the formula shown once. The positional encoding at position pos for an even dimension is the sine of pos divided by 10,000 to a power. For the odd dimension right next to it, it's the cosine of the same thing. Decode the symbols. Pos is which word 0, 1, 2, I indexes the dimension. Even dimensions use sine. The odd ones use cosine. Sines and cosines paired up. That 10,000 to the power term looks scary, but all it does is make each successive dimension's wave a little slower than the one before. That's how we get the spread of frequencies. Don't memorize it. Just hold the picture, a stack of sine and cosine waves, each one slower than the last. Now let's compute a real one. Let's compute a real positional encoding. Take a tiny model with 4 dimensions, so 2 frequencies, a fast wave at rate 1 and a slow wave at rate 100th. We'll find the stamp for position 1. Dimension 0, the fast sine, sine of 1 times 1, sine of 1, is about 0.84. Dimension 1, the fast cosine, cosine of 1 is about 0.54. Dimension 2, the slow sine, sine of 1 times 100th, sine of 0.01 is about 0.01. Barely moved because this wave is slow. Dimension 3, the slow cosine, cosine of 0.01 is essentially 1. So the position 1 stamp is 0.84, 0.54, 0.011. 4 numbers, a unique fingerprint for the second slot, and every position gets its own. Now the magic step, which is almost laughably simple. Take dog's embedding 0.2, 0.9, 0.5, 0.1, and the position 1 stamp we just computed. Add them dimension by dimension. 0.2 plus 0.84 is 1.04. 0.9 plus 0.54 is 1.4. 0.5 plus 0.01 is 0.51. And 0.1 plus 1 is 1.10. That's it. You just add the 2 vectors, position by position. No multiplication, no extra matrix. Dog now carries both its meaning and its place in a single vector. Here's the payoff side by side. Dog in position 1 is 1.04, 1.44, and so on, the vector we just built. Dog in position 3, we compute PE of 3 the very same way. Sine of 3 is about 0.14, cosine of 3 about minus 0.99, and add that instead, giving a clearly different vector, 0.34 minus 0.09, and the rest. Same underlying dog embedding, but a different positional stamp added, so the 2 come out as distinct vectors. And now, because each dog is different, the query, key, and value that attention computes are different too. So dog chase cat and cat chase dog finally produce different results. The order problem from our hook solved with nothing more than a single vector addition. Why waves at different frequencies specifically? Think of a car odometer or counting in binary. 00001 0001 0001. The rightmost digit flips on every single step, that's high frequency. The leftmost digit flips only rarely, low frequency. And that combination is powerful. Just a handful of digits, each ticking at a different speed, can count up to enormous numbers, with every number getting a unique pattern. Sinusoidal positional encoding is just the smooth, continuous version of that odometer. Fast waves and slow waves together hand every position its own unique code. And there's a bonus the designers were after. Because of how sines and cosines relate, the model can recover relative distance, that two words are 3 apart, from simple relationships between their encodings. Relative position comes for free. Let's bust the natural misconception. It's tempting to think the model gets handed the position as a number, a little label reading word number 5. It doesn't. It never sees an integer at all. It receives a smooth pattern of sine and cosine values added directly into the meaning vector. And there's no separate position slot tucked away somewhere. Meaning and place are mixed into the very same numbers. The model learns during training to pull them back apart. Elegant and a little mind-bending. Quick one for the comments. Can you think of 2 sentences built from the exact same words, but with opposite meanings? Dog chased cat versus cat chased dog was mine. Drop yours below. Word order does far more work than we usually notice. And these are precisely the cases positional encoding exists for. Let's put all 3 moves together for one word. We'll trace dog in a dog chased a cat, sitting at position 1. Step 1. The embedding lookup from the vectors video. Dog becomes 0.2, 0.9, 0.5, 0.1, its meaning vector. Step 2. Compute the positional encoding for position 1 from the waves 0.84, 0.54, 0.01, 1. Step 3. Add them together dimension by dimension to get 1.04, 1.44, 0.51, 1.10. Step 4. That combined vector is what actually flows into the attention layer from the attention video, carrying meaning and position at the same time. And this happens once for every word, right at the start before the very first attention layer touches anything. Embed, encode, add. 3 moves and word order is now baked permanently into the numbers. Pause and screenshot the whole video on one screen. A word becomes an embedding for meaning. Then we add a positional encoding for place, and that sum is what enters attention. Why we need it. Attention is a weighted sum, so without a position signal, it's completely order blind. The signal itself, sine and cosine waves at many frequencies, giving every position a unique stamp. How it's applied, you simply add the encoding to the embedding, meaning and place fused into one vector. And the big idea, position becomes part of the same geometry the model already uses for meaning. One more thing, what modern models actually use. The sine waves we built are the original from the 2017 Transformer paper, and the field tweaked it twice. First, learned positional encodings. Skip the hand-designed waves and just let the model learn a vector for each slot, the way the original GPT did. Dead simple, but it locks you to a fixed maximum length. Run past it, and there's simply no encoding for position 5001. And that's a weakness fixed sine waves share too. Neither one generalizes gracefully past the lengths it saw in training. The second, now dominant approach, Rotary Positional Encoding. The idea is gorgeous. Don't ADD a position vector at all. Instead, rotate each word's vector by an angle proportional to its position. Rotating bakes relative distance straight into the dot product's attention already computes 2 words 3 apart always sit at the same relative angle anywhere in the text. And it extends gracefully to very long contexts, which is why most modern models, Llama and friends, use it. But notice, the goal never changed from our sine waves, stamp order onto the words. RoPE is just a sharper tool for the same job. Let's lock it in. 1. Attention is order blind. On its own, a weighted sum can't tell dog chased cat from cat chased dog. 2. Positional encoding fixes it. Sine and cosine waves and many frequencies give every position a unique stamp, which we add to the embedding. 3 meaning in place end up in one vector computed once before the first layer, and from there attention takes over. So we now have the complete input to a transformer, the embedding for meaning plus the encoding for position, ready to enter the stack. You just learned embeddings and positional encoding, which means, and this is exciting, we finally have every single piece. Next up, a full forward pass. We'll take one token and push it through the entire model, end to end, using everything from videos 1 through 5. This is video 5 of 7. Drop your own same words opposite meaning sentence in the comments, and I'll see you in the next one. A full forward pass where it all comes together.